All right, now we're going to kind of use some of the theory we developed in this section to do a couple of things. One is to find intervals of increasing, decreasing, and constant behavior, and then I guess the other big thing we'll be looking at is looking for relative extrema, so relative mins and maximums. So kind of some guidelines here is if we're given a continuous function on an open interval AB, we're going to find first intervals of increasing, decreasing, and constant behavior. So how do we find these? First thing we want to do is we want to locate all critical numbers, and remember critical numbers where the function was defined at some c, and then we had to determine whether whether the derivative existed. If it didn't exist at that point, then that was a critical number, or the derivative at that particular point was equal to 0. So that's the first thing, is locate all extrema. Then you're going to pick test points around your critical numbers, and that's going to determine whether we are increasing, decreasing, or constant. And then around our critical numbers, if we have like a change from decreasing to increasing, then we'd have a relative minimum, or change from increasing to decreasing, we'd have a relative maximum. So that'd be using our first derivative test. Let's take a look at the first example. F of x is equal to 12x minus x cubed. And what we're going to look for is intervals of increasing, decreasing, and constant behavior, and we're also going to look for any relative extrema, any relative mins or max. So first thing we'll do is we'll take the derivative, 12x minus 3x squared, and we're going to set that equal to 0. Now what we're going to do is we're going to divide both sides by 3, and we're going to get, and we'll also add 3x squared to both sides. It'll turn into x squared. So we divide both sides by 3, and then we added x squared to both sides. Taking the square root of both sides, we'll get x is equal to plus and minus 2. So I'll draw ourselves an interval, and our critical numbers are plus and minus 2. Now we're going to test around them. So somewhere in negative infinity to negative 2, we'll test somewhere between negative 2 and 2, and then we'll test somewhere between 2 and infinity. So if we test the derivative at negative 10, it's going to give us something less than 0, so we're decreasing from negative infinity to negative 2. If we test something between negative 2 and 2, like 0, we're going to get something positive, which means we are increasing from negative 2 to 2, and so what we'll have there is we'll have a relative minimum because we went from decreasing to increasing. Okay, and now we'll pick one more number to try. Maybe 10 will fit in that interval from 2 to infinity, and that again will be less than 0, so we're decreasing from 2 to infinity. And we went from increasing to decreasing, so we're going to have a maximum at 2. So I need to find the location of those 2 points, because usually they want to know the location of where these extrema is occurring. So at negative 2, we have to plug in negative 2 into the original function. So if we plug it into the original function, it'll be negative 24 plus 8, or negative 16. And then for the maximum, we'll plug in 2, and we'll have 24 minus 8, which is 16. So our extrema are, we have a minimum at negative 2, negative 16, and a maximum at 2 and 16. Alright, let's look at another function. This function, g of x is equal to x plus 9 over x. We're going to play the same game. We're going to take the derivative. Here's 1 minus 9 over x squared, and we're going to set that equal to 0. We're going to add 9 over x squared to both sides. Multiply both sides by x squared, and we'll have x squared is equal to 9. Take the square root of both sides, and we get plus or minus 3 as our critical numbers. Also, the function is undefined at x equals 0, so we need to take that into consideration when we're writing our intervals of increasing and decreasing behavior. If I say it's decreasing on some interval, it can't include something where it would be undefined. So we need to include 0 as we make our test interval. Alright, So we're going to test between negative infinity and negative 3 to 0, 0 to 3, and 3 to infinity. Chances are within negative 3 to 3 we will have the same sign, either both increasing, both decreasing, but it's undefined at 0. Okay, f prime of negative 10 is going to be greater than 0, so we're increasing from negative infinity to negative 3. F prime of negative 1 is less than 0, so we're going to be decreasing from negative 3 to 0. F prime of 1 is going to be equal to something that's negative, so again it is decreasing from 0 to 3. So you see that it was the same thing. It was either both increasing, both decreasing in that interval, but we can't say it's decreasing from negative 3 to 3 because that implies that it's defined everywhere between negative 3 and 3, and it's not defined at 0. That's why we have to say that. Then we'll test one more time, like 10 on the right of 3, and that's going to be greater than 0, so it's increasing from 3 to infinity. So we're going to have a minimum because we went from increasing to decreasing. Sorry, that won't be it. I have these backwards. I'll have to fix these. So I'm going to write it in, and then I'm going to fix this. I have it backwards. So let me change this right here and right here. So from negative infinity to negative 3, we're increasing, and then we start decreasing after we get past negative 3. So that means this is a max at negative 3. To get the y coordinate, the negative 6, I have to plug that into the original g of x. So then you'd have negative 3 plus 9 over negative 3, and that'll be negative 3 plus negative 3, which is negative 6. Similarly, with the minimum, we went from decreasing to increasing, so we have a min at 3, and then to find the y coordinate, the 6, I have to plug 3 into the original function. 3 plus 9 over 3 is 3 plus 3, that's 6. So be careful about any places where it's undefined. We can't include that in our intervals of increasing and decreasing behavior. Alright, this example is going to need a little bit of trick. We're going to look at the function k of x equals sine squared x plus sine of x, and we're going to look at it on the interval 0 to 2 pi. We'll take the derivative, and we'll need to use the chain rule on the first part. The outside function is the square function, so it's 2 sine, which is the base, to the first power, times the derivative of the base, which is cosine x. Derivative of sine is cosine x. And we're interested in when that's 0. And GCF is cosine x. We'll factor cosine x out. And we have 2 sine x plus 1. And we're going to set each factor equal to 0. So cosine x is equal to 0, or sine x is going to be equal to negative 1/2. Cosine x is equal to pi over 2. Cosine x is equal to 0 when x is pi over 2 or 3 pi over 2. Sine x is equal to negative 1/2. We're going to be in quadrants 3 and 4. That's where the sign is negative. So we're looking at 7 pi over 6 and 11 pi over 6. Okay. I'm going to go to another screen so we have enough room to do all this. So we'll go ahead and set up our interval. 0 to 2 pi is what we're considering, and we're going to put each one of our critical numbers in. And then we'll go ahead and test around them. So f prime of x was equal to 2, well, I'm going to write it in this form, I guess. Cosine x times 2 sine x plus 1, and that might be a little bit easier to tell the positive or negative. Alright, so we're going to test something in the interval 0 to pi over 2. Something easy would be pi over 4. So cosine of pi over 4 is going to be root 2 over 2. Sine of pi over 4 is going to also be root 2 over 2. So we're going to have positive times positive, which is positive. So we're positive in the first interval. In the second interval, we can choose something like pi. Pi is between 1/2 and 7/6. Cosine pi is negative 1. Sine of pi is 0, but we have the 1 in there, so it's going to be negative 1 times 1, which is negative 1, which is less than 0. So we're decreasing in the interval pi over 2 to 7 pi over 6. So it looks like we're going to have a maximum at pi over 2. We go from increasing to decreasing. Okay. Now we'll try something between 7 pi over 6 and 3 pi over 2. So 5 pi over 4 would be good. And that's a 45-degree angle. Cosine's negative in the third quadrant. Same with the sine. Okay. So how I know this is going to be positive is the 2 times the negative root 2 over 2. The 2's are going to cancel. Negative root 2 is larger than 1 in terms of absolute value, so the difference between negative root 2 and 1 will be negative. So I'll have a negative times a negative, which is positive. So I'm increasing from 7 pi over 6 to 3 pi over 2. We're going to have a minimum at 7 pi over 6 because we went from decreasing to increasing. We got to test, let's see, 7 pi over 6. And that's going to be less than 0. And we're going to have maxes at pi over 2, 2, 3 pi over 2, 0. Minimums at 7 pi over 6, comma, negative 0.25, and 11 pi over 6, and negative 0.25. Now it looks like I forgot to test one more point here. We need to test to the left of 11 pi over 6. So let me do that real quick here. So testing one more number between 11 pi over 6 and 2 pi, you can come up with a number and plug it into the derivative function and see what you get. And it's increasing there. So then you just need to write your intervals of increasing 0 to pi over 2, 7 pi over 6 to 3 pi over 2, 11 pi over 6 to 2 pi. Intervals of decreasing would be pi over 2 to 7 pi over 6, and 3 pi over 2 to 11 pi over 6. Alright, let's take a look at another function here. This is the cube root function. So that's one of the parent graphs you probably studied in college algebra and pre-calculus. The minus 3 inside is going to cause it to have a horizontal shift to the right 3 units. We'll go ahead and try this like any other problem. We'll take the derivative. The 1/3 is going to come down, and then we're going to subtract 1 from 1/3 from the exponent, so we'll get negative 2/3 as the exponent. Okay, so 1 in the numerator. There's your 1. Here's your 1/3. Here's your 1/3. And then we subtract 1 from the exponent, so it's going to be a negative 2/3, so it's going to be cube root of x minus 3 squared. And that's not going to equal 0 for all real numbers. So remember, the fraction's only equal to 0 when the numerator is equal to 0. So 1's never going to equal 0. So there are no critical numbers in the sense that we're equal to, the derivative is equal to 0. However, the function is not differentiable at 3. So that's a critical number that we need to consider now. We need to take a look at it. Okay. Now, when I test 0 and 4, on either side I'm going to get positive, and I'll explain why. X minus 3 squared, no matter what I plug in there besides 3, is going to be positive. When I take the cube root of it, it's going to be positive. When I multiply it by 3, it's still going to be positive. So whatever I plug in, it's going to be positive. So it's increasing on both sides of 3. So unfortunately, we're not going to have any extrema here. And if we draw in the cubic function, it kind of has a, well, it does have a vertical tangent at 3. So that's why the derivative at that particular point is undefined, because it has a vertical tangent there. And you can see that the function is always increasing from negative infinity to infinity. So it does not have any extrema, but in terms of increasing and decreasing, we can say it's increasing from negative infinity to infinity. We don't have to worry about the undefinedness because I can plug 3 into the original function. So it's a little bit different than that example we did where it was x plus 9 over x. We had to jump over 3 because it wasn't defined in the original function. Wasn't defined at 0, in the original function. Another parent function from pre-calculus and also college algebra was the absolute value function. So where you're going to take an absolute value function, and the plus 3 is going to shift it left 3, and then the negative 1 is going to shift it down 1 unit. When I take the derivative is going to be equal to negative 1 when x is less than negative 3, because the inside of the absolute value would be negative, so we need another negative to compensate so that the negative and the negative cancel out. If x is greater than negative 3, then we can just drop the absolute value bars, and we just have dx, so we don't need to compensate. So the slope is going to be 1. That's if x is greater than negative 3. So it's not differentiable at negative 3, and we've done an example where the left and the right hand limits don't exist. So from the left of negative 3, it's negative 1. From the right of negative 3, it's positive 1. So it's not differentiable at negative 3, but it is still a critical number, so we can check it out. And all we got to do is we got to use the derivative formula to determine positive and negative. So for the left of negative 3, the derivative is negative. For the right of negative 3, the derivative is positive. So we went from decreasing to increasing, so we have a minimum at negative 3, negative 1. And if we draw the absolute value function, it's just a b at the location negative 3, 1, and you can see clearly that there's a minimum there. Now look, as we are the left of negative 3, we have a slope of negative 1. And to the right of negative 3, we have a slope of positive 1, which is confirmed by our formula. All right, we're going to take a look at one more example from this section, and we're looking at a piecewise defined function. It looks like negative x cubed plus 1 if x is less than or equal to 0, and then it looks like negative x squared plus 2x if x is greater than 0. Now, in terms of the derivative, I'm going to have to break it up into the two branches also. Now, the function's discontinuous at 0 because if I plug 0 into the top branch, I get negative 0 cubed plus 1, so I get 1 for the left side. However, if x is greater than 0, then we use the negative x squared plus 2x, and if I plug 0 into that, I'm going to get 0. So the left branch is going to equal 1, and the right branch is going to equal 0 as I approach 0 from the left and the right. So it's discontinuous there. In order for us to have critical numbers, we had to be we need to look at continuity at that particular value. So we're not going to have a critical number at 0, unfortunately, despite what our table tells us. So I take the derivative. It's going to be negative 3x squared and negative 2x plus 2 for x greater than 0 and x less than 0 and x greater than 0 for the two branches there. And we lose the less than or equal to because of the discontinuity there. If it was differentiable at 0, then the two branches should have linked up, but they don't. And differentiability implies continuity, so that also be bad. So we can't have it equal to 0 on either branch. And we're going to say it's not differentiable at x equals 0. So we're going to still take a look at it and see what it looks like. The only time the top branch is equal to 0 is when x is equal to 0. So we can't do that because it's not differentiable at 0. However, we can look at the bottom branch. The bottom branch is equal to 0 when x is equal to 1. So go ahead and do our critical numbers. I can read right off the branch here. If I plug in like negative 1 million into the top branch, negative 3 times negative 1 million squared is going to be a negative times a positive, which is a negative. If I plug something in between 0 and 1, like a half, I'm going to use the lower branch, which is negative 2x plus 2. So that'd be negative 1 plus 2, so it's positive in between 0 and 1. And then to the right of 1, if I plug in something like negative 1 million, or not negative 1 million, but we have to plug in 1 million, negative 2 times 1 million is going to be a very large negative number. So it's negative to the right of 1. So there would be your intervals of increasing, decreasing behavior. Again, f is discontinuous at x equals 0, so we do not have a min or a max there at 0. And even though it's going from decreasing to increasing, we think, oh, okay, well, you know, it's got a minimum there, but it does not because it's discontinuous. We need that continuity in order for this to work. But we do have a maximum at 1, 1. And we could draw a picture on the next slide to give you an idea. So we have a cubic function that's defined to be 1 at 0. And then we have this parabola with a vertex at 1. And you can see that it's discontinuous. In order for me to be a minimum, I should be decreasing to a point and then increasing. Well, I can't jump down because all of these points down here, they're smaller than at once. That can't be a minimum. Minimum means it's got to be the smallest. So here's an example where continuity is definitely needed in order for this to work.